So ionic versus covalent bonds, bonding pairs versus lone pairs. Next, we're going to go into predicting the relative electronegativities of atoms. We first saw this idea of electronegativities in Chapter 8, Part 2, but we really didn't look at electronegativity. We just looked at ionization energy along with electron affinity or attachment. Electronegativity is somewhat similar to the electron affinity or attachment, but it's not quite the exact same concept. So let's go into this now. So electronegativity is defined as the ability of an atom to attract toward itself the electrons within a chemical bond. Electron affinities, like we saw in Chapter 8, those are measurable quantities, and chlorine has a really high electron affinity. Similar but slightly different is the electronegativity. Electronegativities are relative to one another. So for instance, we look at the electronegativity of fluorine versus hydrogen. So these are relative values, whereas electron affinities could actually be numerical values that are measurable. And again, electron affinity is adding on an electron to a neutral atom to form that anion. When we're thinking about electronegativity, though, we're thinking about the relative ability for an atom to attract electrons towards itself within a chemical bond. So we think of this in a relative way, for example, because we can compare hydrogen and fluorine that are within and sharing a chemical bond. Electronegativity describes the ability of an atom to attract electrons towards it within a bond. So relatively speaking, does hydrogen have a greater electronegativity than fluorine because they're sharing a bond right here? Fluorine has a much higher electronegativity relative to hydrogen because it wants to hog those electrons closer to itself. This bond here, the two electrons that are within that bond here, fluorine has a greater electronegativity, so it wants to pull those two electrons, that electron density, closer to its atom compared to hydrogen. When fluorine is in a bond with any other atom, fluorine is always the most electronegative. It's the most electronegative element there is. So within a covalent bond, fluorine will always pull more electron density towards its atom. Because of the high electronegativity of fluorine, this leads to an electron-rich region on the fluorine side of the atom, or on the fluorine side of this molecule near the fluorine atom. Then because this electron density is pulled this way, that leaves the hydrogen side of this HF molecule slightly electron deficient or electron poor. Just like atomic radii, ionization energy, and electron affinity, there is a set trend we can look at for electronegativities in the periodic table. So we'll look at that in just a moment. Before getting into that, let's connect electronegativity to these covalent bonds. Within this category of covalent bonds, we can have a polar covalent bond. A magnet has polarity to it. The poles of the Earth have polarity to them. Polarity means a separation of positive and negative charge. So for something to be in a polar covalent bond, or just called a polar bond, means we have some separation of positive and negative charge. This is not the same thing, though, as an ionic compound. Ionic compounds have a transfer of electrons. In a polar bond, they're still sharing that pair of electrons. But in a polar bond, a polar covalent bond, there's an uneven sharing of electrons. This uneven sharing of electrons leads to more electron density around the more electronegative atom of fluorine, and less electron density around the less electronegative atom of hydrogen. So it's not a full ionic compound like NaCl, for example. It's still a molecular compound, and so instead of seeing this full charge of Na plus and Cl minus, this means we have a partially positively charged region. So this symbol here means we have a partial positive charge towards the hydrogen, not a full-on positive charge. It's not acting like a cation here with a full positive charge, where that atom has lost an electron. It's still sharing electrons. It hasn't lost any electrons. That's why it has a partial positive, not a full-on positive, but a partial positive region. Similarly then, fluorine will have a partial negative region. It's not a full-on anion. It's still sharing electrons. It hasn't gained any electrons. So it's still sharing electrons, but it's sort of hogging more of that electron density towards itself, so that this region here is partially negatively charged. This region here near hydrogen is partially positively charged. When we get into electron geometries, we'll see this idea of a molecule having a linear geometry. At this point, what we can say is that electron density is greater around the fluorine atom instead of it being equally shared between the two atoms. For electron density to be equally shared, that's considered a non-polar bond. When we have polarity, we have an uneven sharing of electron density between the two atoms. So because the fluorine atom has more electron density, the fluorine side of the molecule is said to be electron rich, whereas the hydrogen side of the molecule is said to be electron poor. Again, because fluorine is more electronegative than hydrogen. When there is a difference in the electronegativities of the two atoms, that's when we have a polar bond. If the two atoms in a bond have very similar electronegativities, that's when we have a non-polar bond. So atoms having a similar electronegativity, they'll have an essentially non-polar bond. One atom isn't going to pull more electron density towards itself, but when there is such a difference in the electronegativity of the two atoms in a bond, it's going to have a polarity to it. There's going to be polarity to it. There's going to be a polar covalent bond when those two atoms have such a difference in their electronegativity values. So let's look at these trends of common elements and their relative electronegativity values. So fluorine's electronegativity is the largest, it's 4.0. When it was bonded with hydrogen with an electronegativity of 2.1, there was definitely a polarity to that bond. Because more electron density would go around the fluorine, it's more electronegative than the electron density around the hydrogen because that's less electronegative. This text down here is a reminder of our valence electron numbers. So 1 valence electron, 2, 3, 4, 5, 6, 7. In group 6A, for example, we know these all have 6 valence electrons. And as we're going to be drawing more and more Lewis-Dot structures, just another reminder on how we draw in those 6 valence electrons for oxygen. We'd represent this as 1, 2, 3, 4. So we go all the way around first. Then we double up with 5, 6. So oxygen with 6 valence electrons is shown like this. Oxygen also has a fairly high electronegativity value of 3.5. These electronegativity values, they're all relative to one another. So it's sort of this arbitrary scale where fluorine has a relative electronegativity value of 4.0. This isn't really a measurable value, it's just a relative quantification. So if the highest value here is 4.0 for fluorine, then something like potassium has a really low electronegativity, so 0.8. it's not going to want a lot of electrons around it. It has a really low electronegativity. So another trend we can look at on the periodic table is we increase relative electronegativity from left to right, and we increase relative electronegativity going up a group or up a column. So if it increases this direction and this direction, it makes sense that fluorine has a very high, the highest electronegativity value. And so here's another way to look at that trend. We have atomic number here and the relative electronegativity. We see fluorine has the highest. So generally, electronegativity increases across a row and decreases down a column or increases up a column. Our transition metals do introduce some exceptions to our general trend, but again, we're focused on the predictable trends we can see with electronegativity. And in general, we're looking at the more predictable trends and less on the exceptions. Halogens are the most electronegative elements, like we see here: fluorine, chlorine, bromine, and iodine. They want to pull in electron density closer to their atom. The goal with electronegativity for all these atoms is still to fill its complete octet. The halogens will have a complete octet when they form a bond with another atom. They already have 7 valence electrons around them for the halogens. So clearly they want to pull in electron density towards their nucleus. Alkali metals, however, that will form those +1 cations, they wanted to get rid of an electron. When they get rid of an electron, they become +1 charged. That means that alkali metals really have very low electronegativities. They don't want to pull in electrons closer to the nucleus. They'd rather give away an electron to become a +1 cation. And so in using these numbers of the relative electronegativities, we can predict the kind of bond, the category of bond between two atoms. For instance, for HF, this electronegativity is 4.0, this one is 2.0. Or not 2.0, but 2.1. Then fluorine is 4.0. The difference in electronegativities, so 4.0 minus 2.0 is about 1.9. This difference in electronegativity falls in the range of a polar covalent bond. We'll see more electron density around fluorine with a higher electronegativity compared to the electron density around hydrogen with a lower electronegativity. If the difference in electronegativities becomes greater than 2, that's when we actually get into the region of ionic bonds. Let's look at an example here for 2 atoms that we know form an ionic bond. For ionic bonds, that will be a metal and a non-metal. Let's look at sodium chloride for an example. We know that's an ionic compound. Sodium is a metal. It has an electronegativity of 0.9. Chlorine is a non-metal. Its electronegativity is 3.0. 3.0 minus 0.9 is about 2.1 difference. That's why this is an ionic compound. There's such a large difference in electronegativity between sodium and chlorine. So as we see very large differences in electronegativity, that's when we're getting into the range of ionic compounds. HF is almost there. There's a really big difference, and we know HF is not an ionic compound, but HF is an acid. The difference in electronegativities leads to the dissociation of hydrogen from HF pretty easily because it is an acid. So HF will dissociate into H plus and F minus. It's an acid. The electronegativity difference between H and F allows for this fairly easy dissociation between the 2 atoms. So for ionic bonds, that's the greatest difference in electronegativity between 2 atoms. For ionic bonds, we don't have a sharing of electrons, we have a complete transfer of electrons. So it's not really a bond, it's a bond in quotes for ionic bond, because it's a transfer of electrons and not a true sharing of electrons. Then for covalent bonds or nonpolar bonds, where the electronegativity difference is 0, that's a covalent nonpolar bond. In covalent bonds, that's a true sharing of electrons. What's a scenario where we might see a 0 electronegativity difference, where we have a true nonpolar covalent bond? Well, for that to work, we could basically put any of our Brinkelhoffs together. For example, 2 bromine atoms. What's the nature of this bond between bromine with an electronegativity of 2.8, this bromine also the same electronegativity value? 2.8 minus 2.8, that's an electronegativity difference of just 0. That means this is a nonpolar covalent bond between the 2 bromine atoms. We won't see more electron density around this bromine atom or around this one. It's a true sharing of electron density. Their electronegativity difference is just 0 because it's the same atom on both sides of the molecule. Then if we do have some slight difference in electronegativity, that's when we get into polar covalent bonds. We have some region of more electron density around one atom and less electron density around the other atom. So like we saw that for HF. So this is considered a polar covalent bond. There's a partial transfer of electrons, but they're still sharing electrons. It's not an ionic bond. There's not a complete transfer of electrons. They're still sharing electrons, just somewhat unevenly. So fluorine is sort of hogging more of that electron density than hydrogen. So it's a partial transfer, but not a full transfer. They're still sharing electron density within that bond between the 2 atoms. And so again, as mentioned, these covalent bonds where there's a 0 difference in electronegativity between the 2 atoms, that's what we call a nonpolar bond. To have polarity means we have some separation of charge. For nonpolar, we have no separation of charge. So no separation of positive or negative charge. We won't have any partial negative or partial positive charge, where those symbols again are partial positive and partial negative. With 0 difference in electronegativity, we won't have any partial charges, we just have a full sharing of electrons and an even sharing of electrons. So here's some general guidelines on predicting relative bond polarity. We can definitely use this table here. For bonds to be considered nonpolar, it's technically anything less than about 0.5 difference in electronegativity between the 2 atoms. So a little bit of a gray area here between 0 and about 0.5, really up to a difference of 0.5 is still essentially nonpolar. But again, we're not really focused on these gray areas. We're just focused on the bigger picture of nonpolar versus polar versus ionic. And so as we know, the greater the difference in electronegativities, the more polar that bond is. Then with a really large difference in electronegativity, that's essentially an ionic bond. So if that difference in electronegativities gets really large, then we're basically just dealing with an ionic compound where we have a full transfer of electrons rather than a sharing of electrons. And so in a pair of 2 atoms, the one atom with a higher electronegativity will be on the negative side of the bond. If you go on to take more chemistry, you'll see this word dipole. Here we're not worried about dipoles. Dipole comes from polarity, so a dipole moment is again just a difference in charges. So a dipole moment, a region of negative charge and more positive charge. And so as we saw those trends in electronegativity, where it increases going up a column and it increases going left to right. An element to the left of another element in the same period or row then would have a smaller electronegativity compared to an element that's to the right of it. Again, just looking at within the same row or period. And since electronegativity increases as we go from left to right along a period, the electronegativity difference, and hence the bond polarity, how polar is that bond? The bond polarity will increase the further to the right a certain bonding partner lies. So comparing an element here with an element here, that's a pretty large expected electronegativity difference than just comparing an element here versus here. So let's practice with this idea of electronegativity, and we're going to reorder each list of elements in this table if necessary so that the elements are listed in order of decreasing electronegativity. So the highest electronegativity, or denoted as En, then going to the lower of the electronegativities. And again, electronegativities are relative to one another. They are not measurable absolute values. So let's look at the relative difference in electronegativities between these three and these three, given the trends we know about on the periodic table. And so we've looked at HF quite a bit. It turns out that the shared valence electrons in the HF bond right here are not shared equally. In fact, those electrons spend much more time orbiting closer to the fluorine nucleus because fluorine is way more electronegative. So we could even say that fluorine sort of hogs the electrons in that HF bond. Rather than saying that fluorine hogs those electrons in the bond, we say that fluorine is more electronegative than hydrogen. And so on a relative scale of electronegativities, hydrogen has a value of about 2.20 or 2.1 for its electronegativity. Fluorine about 3.98, or as we saw, about 4.0. The electronegativity is a numerical rating of the power of an atom, the power that it has to control nearby valence electrons. How much can it hog nearby valence electrons? And so when two atoms are chemically bonded, the atom with the higher electronegativity has greater control over those shared valence electrons in a bond. When we think about electrons in an ionic bond, there's just a full, complete transfer of electrons. So chlorine with a much higher electronegativity than sodium will definitely hog those electrons to the point where there's even just a full transfer of electrons to the chlorine from sodium. There's one electron transfer from sodium to chlorine. Sodium will give up one electron, chlorine will gain that electron. So this is the case for ionic bonds. We have been looking at covalent bonds too, and those can have pretty strong electronegativity differences as well. Another way to visualize the relative electronegativities of atoms in the periodic table is here. In this representation, the higher the electronegativity, the higher the element is drawn, sort of in this vertical 3D image. So there are four basic rules to be familiar with about electronegativities. The first is that fluorine has the highest electronegativity of any element on the periodic table. Next, electronegativity usually increases as we go up a group. Also, electronegativity usually increases as we go to the right or across a period or row in the periodic table. Because we think about electronegativity differences, especially within bonds, we actually don't usually assign noble gases a value for their electronegativity. They already have a happy complete octet. They don't like to participate in bonds because they don't need to. The reason for atoms to participate in bonds is to reach a happy octet or duet. The noble gases have already achieved that, so again, they're fairly unreactive. They don't like to participate in bonds because they already have a satisfied complete octet or duet. So we don't really think about electronegativity values for our noble gases. Electronegativity values help us think about the electron density shared within a bond. But if noble gases don't generally participate in bonds, that's why they don't usually get a value for their electronegativity. So like we see here, fluorine has 4.0, but we don't even have assigned values for these noble gases. We can assign electronegativity values for these two noble gases, but again, generally these don't like to participate in bonds. So for our practice problem, we're looking at the difference between these three and these three. In deciding which of the elements has higher electronegativity values without even knowing their exact values, we can think about those trends on the periodic table. We see an increase in electronegativity in this direction and an increase in electronegativity from left to right. So I'm looking at nitrogen, carbon, and oxygen first. Oxygen is on the right-hand side, carbon is on the left-hand side. Remember, electronegativity increases from left to right. So carbon would have the lowest value, then nitrogen, then oxygen. We just needed this idea of a general trend. We didn't need to know their exact values for the practice problem we're working on. For some other examples here, if nitrogen is higher up than phosphorus, then nitrogen will have a higher electronegativity value than phosphorus because nitrogen is above phosphorus on the periodic table. So here's nitrogen above phosphorus on the periodic table. And again, we know electronegativity increases going up a group. Then comparing nitrogen versus boron, nitrogen will again have the higher electronegativity than boron because it's towards the right. It's to the right of boron, and electronegativity increases going left to right. Then another example here, nitrogen has a higher electronegativity than germanium because nitrogen is to the right and it's up from germanium on the periodic table. So nitrogen here versus germanium, for both reasons of this trend, nitrogen has a higher electronegativity than germanium. And so again, our transition metals do introduce some exceptions, but we are focused on the predictable trends here. We're also going to just be comparing within one group or within one row. It gets trickier if we're trying to compare one element here with one element way over here. So our trends hold, especially if we're looking at within one group or column and within one period or row. A comparison of nitrogen and germanium is a fair one to make as well, because either way we look at it, nitrogen is higher up in the periodic table and it's further to the right. But making a comparison between titanium, for example, and something like tellurium, that's a harder difference to do because these are so far apart and they're not even within the same period or in the same group. So we won't be looking at comparisons like that. If we did, we'd need to look at the periodic table where we're given actual values for electronegativity. And so again, that table would be here if we needed to compare more difficult instances like titanium and tellurium, for example. So we're also looking at S, E, S, and O. That's for our second problem here in this practice problem. So here's sulfur, here's selenium, and here's oxygen. If electronegativity increases going up a group, we know that selenium will have the lowest value, oxygen the highest. So we're told to list these from highest to lowest values. Highest is going to be oxygen, then sulfur, then selenium. So here's oxygen, sulfur, then selenium. For our first row, we decided that oxygen has the highest electronegativity. It's furthest towards the right. Then next highest is nitrogen. Then the lowest of these three is carbon. It's further to the left in the periodic table. And so just to show that here again, here's carbon, then nitrogen, then oxygen. So lowest, middle, then highest electronegativity. For another example to look at, you can see example 9.2 in the main slide deck for more on electronegativity. Next, let's go into this topic, so counting valence electrons in a molecule or polyatomic ion. We've focused on valence electrons so far, mostly as, for example, the halogens having 7 valence electrons, the alkali metals having 1 valence electron, alkaline earth 2 valence electrons. Because these have 1 valence electron, they like to get rid of that valence electron to become +1 cations. The alkaline earth metals like to get rid of 2 electrons to become +2 cations. Now we're going to look at valence electrons, but within a molecule or a polyatomic ion. To do this, we still need knowledge of the valence electrons for each specific atom. And so to formally define these valence electrons, they're the electrons in the outer shell. The valence electrons are the electrons that ultimately end up participating in chemical bonding. 1A, our alkali metals have 1 valence electron. Group 7A, our halogens, have 7 valence electrons. For their electron configuration, it's what we'd expect. So for those alkali metals, they'll have 1 electron in the s orbital. Alkaline earth metals, 2 electrons in the s orbital. Halogens will fill that s orbital, then have 5 electrons in that p orbital, or in that set of p orbitals in that p subshell. So we still need this knowledge of different elements in different groups and how many valence electrons they have. We'll need this because when they start to form and participate in bonding, they're still going to come in carrying this initial amount of valence electrons. And so as we've looked at a little bit, so for example, oxygen we saw has 6 valence electrons. So to draw those around this chemical symbol for oxygen, it's 1, 2, 3, 4. Then we double up 5, 6. For carbon, that has 4 valence electrons. We just draw the element symbol, then 1, 2, 3, 4 valence electrons. So based on each atom's number of valence electrons, we can denote each one like this. Hydrogen, lithium, and sodium, all of our alkali metals just have 1 valence electron, so we just depict it like this. The electron being in this spot, or up here, or on the left-hand side, that's all the same thing. Then similarly, this is the same thing too. So 2 pairs, then 2 singles around the oxygen. This is the same thing as this, just looking a little bit different. But just 6 valence electrons in total for oxygen. So again, these are basically the same thing, they just look a little bit different. And so as we saw for groups 1A through 8A, we do know their valence electrons. We don't usually look at the valence electrons in the transition metals, so just for group 1A, 2A, then 3A through 7A. All of our noble gases, except for helium, which has a duet. So just with a duet with 2 valence electrons, looks something like this. It usually doesn't like to participate in bonding, so if it did, we might see it like this. But helium is already happy and satisfied with a duet, so we can really draw those 2 electrons on any side of the element symbol. Then our other noble gases that do have a full octet, we just see that like this. So for argon, for example, 1, 2, 3, 4, 5, 6, 7, 8. They don't need any more valence electrons to have a happy octet, so we can denote these noble gases like this. Halogens with 7 valence electrons, what can they do to have a happy octet? They'll gain an additional valence electron by participating in a bond. Our alkali metals like potassium, how can that be happy with a complete octet? Well, it wants to get rid of 1 valence electron to reach a happy octet. So these elements will sort of participate with one another so that they all have happy complete octets or duets. The conversation might be, hey, I will give you one of my valence electrons so you can have a happy complete octet because I need to get rid of one and I know you need an extra one. So that'd be something like potassium talking to fluorine. So again, we've practiced counting valence electrons, but for individual atoms. Now let's try this practice problem of determining the number of valence electrons, but in this polyatomic anion. O2, 2-, this is a peroxide ion. So valence electrons are electrons that can form chemical bonds to reach that happy octet or duet for each atom that's participating in a bond. We can count the number of valence electrons in a molecule or polyatomic ion by keeping these guidelines in mind. The first is that every electron that's a valence electron in an atom is also a valence electron in a molecule or ion formed by that atom. So for instance, for carbon, an atom of carbon has 4 valence electrons because of its placement on the periodic table. Here's carbon in group 4A. Carbon itself has 4 valence electrons, and in a molecule like carbon dioxide, or in a compound, I should say, the carbon atom in this compound must also still contribute 4 valence electrons. It contributes these valence electrons to the whole carbon dioxide compound. Similarly, oxygen is coming in with 6 valence electrons. There are 2 of them. So carbon with 4 valence electrons, each oxygen with 6 valence electrons, that totals up. So 12 plus 4, that's 16 valence electrons in the whole compound of carbon dioxide. Then guideline number 2, an electron that is added or subtracted from a molecule to make a polyatomic ion is assumed to be one of its valence electrons. Valence electrons are the electrons in the outermost shell, so the highest value for N. Electrons in lower levels of N are closer to the nucleus. They will not participate in bonding. It's the valence electrons in the outermost shell that will participate in bonding. They're further from the nucleus. They have more flexibility to be shared between atoms. So let's follow these steps for our practice problem at hand. So O2, 2-. The first thing we want to do is add up the valence electrons from each atom that forms the molecule or ion. So in ignoring this charge here for a second, we'll come back to that. That's 1 oxygen and a 2nd oxygen. Based on oxygen's placement in the periodic table, we know oxygen has 6 valence electrons. It's in group 6A. So this atom has 6 valence electrons. There are 2 of them, so that's another 6 valence electrons. Here in this step right now, we know there are at least 12 valence electrons. Again, though we haven't dealt with this charge here on the ion, it's an anion. It must have gained 2 additional electrons. Right now we just counted up O2, so 6 and 6 for 12 total, at least at this step 1. Next, we do need to account for that charge. We need to add or subtract valence electrons to account for the charge on the molecule. For example, if the molecule has a -1 charge, like nitrate, for example, that has 1 additional valence electron that's been added to that molecule. Similarly, if the molecule has a -2 charge, 2 additional valence electrons need to be added to the total. So that's something like sulfate, SO4, 2-, 2 additional valence electrons on top of the valence electrons from sulfur and 4 oxygens. But we don't always work with just anions, right? We can also see cations. If the molecule or ion or compound has a +1 charge, we need to subtract 1 valence electron from the total. If the molecule has a charge of +2, we need to subtract 2 valence electrons from the total. One example of this is ammonium, so NH4+. We find the valence electrons in 1 nitrogen and 4 hydrogens, then subtract 1 electron from the total because this has a +1 charge. For our example right here, O2, 2-, that has a 2- charge. We are building up to drawing Lewis dot structures. At this point, we do need to feel really comfortable counting the number of valence electrons. For just O2 on its own with no charge, that is 12 total valence electrons. We don't have just regular O2, just regular diatomic oxygen. We have O2, 2-. This is 12 valence electrons plus 2 more valence electrons that are causing this to have a 2- charge. This means in total, this polyatomic anion will have 14 valence electrons, 12 plus 2. 12 valence electrons from the O2. Because it's O2, 2-, that's an additional 2 valence electrons, totaling to 14 valence electrons in total. Again, this is a really important skill going into drawing Lewis dot structures, so we need to take this step slowly and definitely make sure we understand if it's a -2, that's 2 additional valence electrons. If it's +1, that's 1 less valence electron. So we're going to be careful here, especially as we transition into drawing those Lewis dot structures for ourselves. So for this polyatomic anion, we did figure out there are 14 valence electrons in total. I'm going to include these animations here on covalent, ionic, and ionic versus covalent bonds. If you have any questions at all, let me know. I will talk to you more next time for more on Chapter 9. I'm also including here some animations that are copyrighted and they are provided by the publisher.
Sodium and chlorine are examples of atoms that combine ionically. Sodium is a reactive, soft, silvery metal of low density. Its atoms have 1 valence electron. Chlorine is a corrosive, yellowish-green gas. Its atoms have 7 valence electrons. When mixed, the 2 atoms combine explosively as an electron moves from each sodium to each chlorine atom. A closer look at the resulting product reveals the formation of small white sodium chloride particles, also known as table salt. Water is an example of a compound containing 2 oxygen-hydrogen covalent bonds. Hydrogen is a colorless, explosively reactive gas. Its atoms have 1 valence electron. Oxygen is a colorless, reactive gas. Its atoms have 6 valence electrons. When the 2 gases are mixed, a spark will cause them to react. The atoms explosively combine as a pair of electrons become shared between each oxygen and 2 hydrogen atoms. A closer inspection of the inside of the container shows water vapor condensed on the cool container walls. Here is the same reaction in a different setting.
When forming compounds, atoms tend to gain, lose, or share electrons to achieve a stable noble gas electron configuration, an octet of electrons. In ionic bonding, an octet is formed by transferring 1 or more valence electrons from one atom to another. In covalent bonding, an octet is formed by sharing valence electrons between atoms. Sodium has 1 valence electron and fluorine has 7 valence electrons. If the 1 valence electron of sodium is transferred to fluorine, both atoms achieve an octet of electrons. By losing 1 electron, sodium has a +1 charge. By gaining 1 electron, fluorine has a -1 charge. An ionic bond is the electrostatic force that holds ions together in ionic compounds. Both fluorine atoms have 7 valence electrons. If 1 electron from each fluorine atom is shared with the other atom, then both fluorine atoms achieve an octet of electrons. This type of bond is called a nonpolar covalent bond. The sharing of electrons between atoms is exactly equal, and the electron density is symmetrical. The distribution varies according to the colors of the rainbow. The most electron-rich region is shown in red, in this case the region between the 2 nuclei, and the most electron-poor region is blue. Hydrogen has 1 valence electron and fluorine has 7 valence electrons. If the 1 valence electron of hydrogen is shared with 7 valence electrons in fluorine, fluorine achieves an octet of electrons. Note that hydrogen has only 2 electrons, which is the electron configuration of helium. When bonded to another element, hydrogen will have 2 electrons in its valence shell. In this bond, fluorine has a greater attraction for the electrons in the bond, a greater electronegativity. Because the electrons spend more time near the fluorine atom, the electron density shifts towards fluorine. The most electron-rich region is red, the most electron-poor region is blue. The result is a greater electron density near fluorine, a partial negative charge, and a correspondingly lower electron density near hydrogen, a partial positive charge. This type of bond, where bonding electrons are unequally shared, is called a polar covalent bond. A polar covalent bond can be thought of as an intermediate between a nonpolar covalent bond and an ionic bond.
A covalent bond consists of a pair of electrons shared by a pair of nuclei. Let's use this graph of potential energy versus the distance between the nuclei to see the change in energy as the distance decreases. We'll pay most attention to the bond in H2 and then look at Cl2 and larger halogens, defining 2 key bond parameters along the way. When the H atoms are far away from each other, we designate the energy as 0. As they move closer together, they attract each other more and more, and the energy decreases to a minimum. At this point, a stable hydrogen molecule is formed. If the nuclei come any closer, the energy increases rapidly as nuclear and electron repulsions take over. Now let's zoom in closer to see the overlapping atoms in more detail. When the atoms are far apart, they do not feel each other. But as they come closer, the nucleus of one atom attracts the electron cloud of the other, and the attraction draws the atoms still closer. Note the increasing electron density between them. Soon, the electron clouds interpenetrate. Attractions dominate, but repulsions between nuclei and between electrons become stronger. At the point of lowest energy, attractions just balance repulsions, and the 2 H atoms exist as an H2 molecule. The covalent bond is the mutual attraction between the nuclei and the electron pair. If the nuclei were to move closer, repulsions would outweigh attractions. The increase in potential energy would destabilize the system and the atoms would move apart again. In reality, the molecule vibrates, the atoms moving slightly farther and closer at the point of minimum energy. The bond length is the average distance. For H2, it is 74 picometers. The bond energy, the difference between the minimum energy and the starting point, is the energy needed to break a mole of H2 molecules into separate H atoms. For H2, it is 432 kilojoules. Now let's compare H2 with Cl2 and other halogen molecules. The much larger chlorine atoms reach the energy minimum and form a Cl2 molecule at a greater internuclear distance. Because the Cl nuclei are farther apart, it takes less energy to separate the atoms. thus a greater bond length and a smaller bond energy. Moving down group 7A, bromine is larger still, so we would expect an even greater bond length and smaller bond energy. And iodine, the largest of these halogens, continues the trend to longer, weaker bonds. Stepping back, we see that in each case, mutual attractions draw the atoms together and they form a covalent bond of specific length and energy.